Today we're hearing from Peter Meehan, and later Will Jones will be joining us for questions. So we're looking at the history of iron, its development and use, and how it relates to the works that they've undertaken on Manchester Town Hall. So first of all, a little film.
Good afternoon, everybody. It's nice to see a nicely group of people interested in what's been happening. I'm here for Heritage Project Contracts. As Sue said, we have been responsible for works mostly to the cast iron and wrought iron elements on the Town Hall. But you may have noticed some gilding going on there. That's on the copper weather vane. So we don't just do iron, but obviously the main focus of what we've done at the Town Hall is iron. So what I'm going to do is give you a little bit of a talk about what is iron, the different types of iron, how it deteriorates, what we can do to stop that process and what the process of conservation involves, and then a little bit about the works that were done to some of the iron elements that we were fortunate enough to work on the Town Hall. So what is iron? Well, it's a metallic element which is obviously silver in colour, lustrous, but it's quite soft, and it's unusual in that it has magnetic properties. It's the sixth most abundant element in the universe, and about 5% of that is present in our Earth's crust. The problem is, though, because it's not a stable metal, it likes to oxidise in air, so you don't normally find it as a metallic element. It always exists as a compound or a mineral in the ground. So the main sources of iron for us are magnetite and hematite, and then you can also get it from siderite and limonite. It's extracted from its ore by a process known as chemical reduction, which, as the name implies, removes the oxygen or the oxides and reverts it back to a metal, as well as removing impurities. And that raw material then is what's known as pig iron. And the process of reducing the iron down to pig iron takes place in what's known as a blast furnace, and that's an illustration of a typical blast furnace structure there. And what you would add is your iron ore, and then you would add limestone, which acts to take out impurities in the form of slag, and then charcoal or carbon, in the form of charcoal, or now as coke. And what you do is you heat it out and blow lots of hot air in underneath. It brings the temperature up to a melting point, which is over 1500 degrees. The reduction process occurs, and you end up with lead forming down in the bottom of the furnace, and then the lighter slag and impurities float on the top, and then the iron is drained off as a molten metal at the bottom. So in simple terms, what we're doing is we're taking the ore, we're relying on the fact that oxygen has more of an affinity with carbon than it does with iron. So the oxygen transfers from the iron to the carbon to give you carbon dioxide, and we get our pure iron as a result of that. And the reason it's called pig iron is because traditionally when it was made, it was run out of the furnace into this big sand bed with all these cutouts in it, and it looked like a sow suckling her piglets. So that's why it's called pig iron. And they used to break the piglets off, and that was your iron. we don't tend to use iron in its pure form because it's not such a good material. So it's always alloyed with another material. And so there are three basic forms of iron that we know of. And there's wrought iron, which is the earliest form of iron, cast iron, and today we obviously have steel and very many different varieties of it. And they're essentially all alloys of iron with different amounts of carbon in them and other trace elements as well. So saying a little bit about wrought iron, it's the earliest form of iron that was worked by man. And as I say, because iron melts at over 1500 degrees, at that time, they weren't physically able to get the temperature up high enough to make the iron melt. So what they did was they would build this little bloomery furnace, put the ingredients in that I mentioned before, and they would get it as hot as possible. And so you get a start of a chemical reduction process, and you get this sort of gelatinous type material forming in the bottom of the furnace. So where they'd open the furnace up and pull this sort of spongy mass out, iron out, with various things, including slags and other things all into it. And that was known as a bloom. So then that bloom was taken out when it was red hot, placed on an anvil or a stage, and repeatedly hammered to drive out the impurities and to consolidate the iron into a more usable mass. And that's where we get the term wrought iron from. And so there's an example there of a piece of bloom that's come out of the furnace, ready to be hammered and worked down into a more substantial solid mass of iron. And one of the characteristics of wrought iron to look out for is it's got like a what we call a grain structure. Because it's hammered and worked and run down, the iron tends to form into slight fibres. So you get like a fibrous structure like wood, and then wraps around those fibres you get the glassy slags, and that's like a characteristic of wrought iron. And sometimes if you look at a piece of historic iron, you'll see it's got what's like a crack or a shake in it, and that's a good clue as to it being wrought iron rather than more modern steel. If you're interested, well, you are interested because you're here. With historic conservation work on iron now, obviously where we can, we like to use wrought iron. One of the drawbacks is that it's not manufactured anymore in the Northern Hemisphere, and it hasn't really been made since the sort of early 20th century. So what we rely on is the recycling of old wrought iron. So what used to happen was, and there's one particular company, they used to buy in lots of scrap pieces of wrought iron, things like sections of ships' chains, anchors, bits of bridge structure. Network Rail and British Rail, over time, they've taken down old bridge structures and things like that to replace them with new. And this iron became available for recycling. So what happens is this company would buy it up. It will be chopped up into little pieces. It will go back to a specialist furnace to be reheated, and then it will be re-hammered down and re-rolled again to make, the sections that are required to do conservation repair. Sort of sadly, as we've gone forward in time, the company that's done that work, the guy who sort of developed it, has passed away. And the supply of sort of historic iron for recycling has reduced quite a lot now, so it's a lot harder to get hold of. So generally speaking now, unless it's really significant as a piece of historic ironwork, the alternative option is to use something called pure iron, which is a material that was developed originally as sacrificial anodes for things like ships' hulls and things like that, to try and prevent that steel from corroding. So there is a sort of growing industry, albeit quite small, of providing pure iron for use in conservation and restoration of ironwork. Generally, we avoid using steel because the two materials are not very compatible with one another. So typically, wrought iron is very low carbon content, about 0.25%, as most of it gets driven out during the working process. And I'd say it's got this fibrous structure, and you get these slag inclusions in there. And there's a lot of belief that the reason that wrought iron is more corrosion resistant than steel is because these glassy materials provide a sort of seal to the metal to a certain extent, And if we look at it under a microscope, you get these sort of straight line structures of the iron fibres with a certain amount of carbon and slag in between. So, say until about the sort of 14th century, production was very small in these little tiny bloomery furnaces. But eventually they developed bigger furnaces, more, cupola furnaces and blast furnaces that can produce bigger quantities. And then those organisations that had lots of money, particularly the church at that time, would, pay for these beautiful pieces of ironwork to be made by blacksmiths, obviously to show off their wealth and status, really. And in terms of its use as a structural material, some of the earliest examples are, again, to do with churches, and one of the ones that's quite well known is there's a reinforcing band around the tower of Salisbury Cathedral, which was put in about the 14th century, and that's made from really substantial pieces of wrought iron. So traditionally, this was worked by a blacksmith. Obviously, they were very skilled individuals, and they would develop ways of producing this really highly decorative pieces of ironwork by, carefully working out how to make pieces and how to fit them together so that you come up with these lovely gates and railings and things like that. And it involved taking your pieces of iron, putting it in the furnace, heating it up to red heat, and hammer it into the shape that you wanted. And then as it cooled, you'd put it back in again and so on, and that process would continue. As you can imagine, it's quite a labour-intensive and time-consuming operation, which obviously by today's standard makes it quite expensive. But there's an example there, some nice 18th century gates from a little church just outside Hereford in a place called Home Lacey. You can see that the sort of fineness of it and the nice amount of decoration that was possible with it. And then next to that on the right, you can see a pair of the portcullis gates at the town hall, which also were made towards the end of the period of when wrought iron was used as a material. And again, these are all highly decorated. There are 4 sets of portcullis gates on the 4 sides of the town hall, all with different decorative features. And then there's a 5th set of gates, which are more traditional, which open as well. And perhaps one of the most famous exponents of the blacksmith's craft was a French gentleman called Jean Tijoux. And he came across in the late 17th century with William and Mary, when they set themselves up at Hampton Court, they employed him to make lots of beautiful iron railings and gates, known and famous now as the Tijoux screens. And a lot of the supporters and wealthy individuals at that time wanted to emanate what William and Mary were doing, so they employed Tijoux to make nice pieces of decorative ironwork for them as well. And a good example of that is the work that exists at Burley House. There's several sets of nice decorative gates there, which were made by Tijoux as well. And the golden gates are perhaps the most famous set that are there today. They are basically gilded iron, so there's a lot of gilding on those. So moving on to cast iron, that was sort of seen as the new material at the time of the Industrial Revolution. It had been made previously over in Asia and in China, but it wasn't really known much in Europe other than for limited things like cannonballs and things like that. But it really took off at the early part of the Industrial Revolution when Abraham Darby I in Coalbrookdale patented a method for making thin cooking pots. And he was able to produce these patterns that allowed uniform pots of different shapes and sizes to be made. And obviously the cost was the thing, and it came down and made these things much more affordable for people. And traditionally cast iron was made using charcoal as the source of carbon, but as the Industrial Revolution developed, supply of charcoal became more difficult. It was produced traditionally by a process of coppers in woodland, and then obviously but burning the wood in a reducing atmosphere to turn it into carbon. But as you can imagine, even though they were coppicing trees, it would take a long time for that to regrow. And obviously it was holding back the development of the industry. So Abraham Darby III, who was the grandson of Abraham Darby, developed this process for doing a very similar thing with coal, where you reduce coal to produce coke in much the same way by taking out all the impurities. Because the problem with coal is the presence of sulphur meant that you couldn't make a good quality iron. And it was only with the development of coke that the growth in the the expansion in the use of cast iron really took off. And that picture at the bottom there is a couple of pigs from the Blaenhaven Ironworks, where a lot of early work in the development of iron, cast iron and steel was undertaken. So with cast iron, the main difference is it's got much more carbon in it, typically 2 to 4%, and then maybe between 1 and 6% of silicone. But it's unlike wrought iron, which has got like a fibrous structure, cast iron has got a crystalline structure, and then that's interspersed with flakes of graphite, which is the thing that introduces the weakness into cast iron and makes it brittle, because that's where it tends to fail. But obviously, it was a great material for reproducing things that look the same in multiple ways. And once your pattern had been made, it was quite a cheap and quick way of mass producing things. There was not so much labour involved as if you were trying to get something made in wrought iron. So it became very popular in the Victorian era. You've got an example there of quite an ornate cast iron fireback, which is one of a pair at Eastnor Castle, just outside of near Hereford, Ledbury Way. And then obviously in its zenith, it was used for all kinds of different things, including firebacks, fire grates, fire surrounds, and stoves and things like that, because it's very versatile material. Obviously, you could make all kinds of different shapes and decorative details depending on what people wanted. There's probably there's 4 different types of cast iron. There's your traditional grey iron, which I've just showed you, which is got flakes in it. It's got good wear resistance and can be machined. Then you've got white cast iron, which has got carbides in it due to it being quick cooling. And often that was used to give you like a hard wearing edge or surface for something. More recently, with a product called ductile iron has been developed. And this is a form of cast iron where just before they get to the point of pouring the molten iron out of the furnace, they add magnesium to it, and that has the effect of causing all the graphite flakes to form into like balls or spheres, which gives it a much different properties, and it makes it much stronger and not brittle. And if you were to look at it under a microscope, you've got your crystals there still, but then rather than flakes of graphite, you've got these spheres. And one of the nice things about it is it's very similar material in appearance to traditional grey iron, but it's much stronger and more resistant. So, an example of today, we might, for instance, on a bridge parapet or something where you might have traditional cast iron panels, if they get damaged and broken because, let's say, they've had a vehicle impact, they might often be replaced with a ductile iron because it's much stronger and more resistant to physical damage. But it looks identical. In order to make something out of cast iron, you need a pattern of the thing that you want to create. So traditionally, they would have been made out of wood. And obviously, as things have moved forward, the materials have changed. And today, they might be made out of MDF or resin or wax or plaster. And increasingly today, we're finding that pattern makers are resorting to 3D printing to make patterns for things. The important thing to remember when you're making something using a pattern is that metals shrink a little bit. So the pattern maker has to make an allowance in his pattern for that shrinkage so that the size is correct when it's made. With cast iron, the shrinkage is approximately about 1%. But it doesn't just shrink in all directions. There are certain planes where it shrinks in preference to others. And obviously an experienced pattern maker will know, let's say for a railing panel or a gate, where the shrinkage might be. Now, in conservation, if we're working on something and you need to make a small repair, or let's say you've got some finials missing on some railings and you want to replace them, the quickest and easiest option is to take an original, make that as your pattern and cast from it. but understanding that you get a little bit of shrinkage occurring. Well, of course, if you're looking at a set of railings, you would never notice that the finial's maybe 2 or 3 millimetres smaller than the one next to it. However, if you scale it up to something like a cast iron column, yes, you can copy cast something that big, but then you have to build that shrinkage into your casting. So you might lose a couple of inches on the bottom of a 6-foot column. So you would then have to put that in somewhere within your pattern so that when it's cast, it's the same length as the one that it's been used to replace. So once you've got your pattern, you then need to make your mould. Traditionally, moulds were made out of what's called green sand, which was a very fine sand with clay in it, which dried to a certain extent and held its shape when you took the pattern out of it. Today, there's only one, as far as I'm aware, there's only one quarry that still mines green sand, and that's near Bromsgrove. But most foundries now use a more traditional type of ordinary sand, but they mix either a resin in it which sets a formaldehyde-based resin, or they'll use a resin where when you blow carbon dioxide gas through it, it sets. What it does, it makes the sand solid enough that it retains its shape for when you pour the molten metal in to make your casting. But once you've finished, you can fairly easily break that sand up to get your casting out afterwards. And for a simple casting, that's the sort of process you would have. It tends to be made in 2 halves with a joint line, and you'd put your pattern in, make 1 half, turn the box over, make the other half. The other things you need to add into your mould are vents for hot gases and airs to come out. Obviously, as you pour your molten metal in, the gas and the air that's in the pattern has to come out. And also, you need to allow a little bit of extra, because as the metal cools, obviously it shrinks down. So you need to add a bit of extra so that as it shrinks down, you don't end up with imperfections in your castings. As to give you a simple example, a cast iron rainwater pipe there. Obviously, if you're casting something with a hole in it, you have to make an allowance for the hole. So we put in the mould what's known as a core, which obviously fills the space, and then you've got a gap between the core and your mould where the metal would run. But that core needs to be removable once you've cast your piece of metal. So often what they do today, the beauty with modern casting sands is that you can make these cores and they're quite strong, but obviously once you've cast your pipe or whatever, it's quite easy to break that core up and take it out. The other thing you need to remember when you're casting something is you can't have any undercuts. If you've got an undercut, then you can't take your mould apart to get your pattern out without damaging your mould. So sometimes when you've got really complicated castings with various shapes to it, you have to have all kinds of extra little bits added into your mould as you make it up so that you can systematically dismantle it, take these pieces out, and then put it back together again. So that's the example of the pipe after it was cast with the core in it still, which is to be removed. An example of a more ornate casting. These were a set of gates that were made for Pittville village in Cheltenham. The original gate pier survived, but the gates, I think, disappeared during the Second World War. And the local community were very keen to have the gates reinstated. And so money was found and replica gates were made and cast in iron. And you can see the sort of basic process there. You've got your pattern sitting in 1 half of the mould, the sand mould there. The second image, you can see that the mould's been taken out after the sand is set, so you've got an impression of half your gate in that. You then repeat that for the other side, put the 2 halves together, making sure that they're nicely lined up. Now, as with any liquid, when you're pouring it into a mould, if you don't have a weight on it, the mould will just float up. So you have to put a huge amount of weight on it to keep it nicely sealed together. And then think for that gate, if you look at those blocks on there, each one of those weighs 25 kilograms. So there's quite a lot of weight on there to stop that pattern from pushing itself apart. So once you've cast your gate panel, then where you've got the joint between the 2 halves of the casting, you get a flash line often where you get a little bit of metal bleeding out slightly. so that needs to be dressed back. And the process is known as fettling, where you carefully cut away some of these excess pieces. And sometimes as well, if you're casting something decorative with holes and pieces in it, you then have to carefully clean out those areas as well to bring out the complexity of the decorative detail. It's the most unpleasant job in the foundry, fettling, basically, because all day long you're grinding away and getting dust. So I don't understand but anyway, it's one of those jobs that has to be done. So thinking finally now onto more modern material, what we know as steel. It has been around for quite a long time. Again, it was something that was first developed in Asia and the Middle East, but it wasn't until the Industrial Revolution again, and particularly in the 18th century, that we got to grips with the manufacture of steel in Europe. And it basically, what you're doing is you're taking a piece of pig iron and you're melting it and reheating it so that you can, by means of reduction, take some of that carbon out. So what you're doing is you're heating it up to molten state, and then you're passing hot oxygenated air over the top, and that causes the carbon in it to react to produce carbon monoxide and carbon dioxide, which brings the concentration of the carbon down in the metal to a level that you want. That was one of the first developments. Was a gentleman from Germany called Carl Siemens, who produced this particular type of furnace, and then that was further developed by Henry Bessemer in 1855 as a process for getting the carbon out of this iron. And many people, one of the places where this was first developed was in Blaenhaven Ironworks in Wales. And many people were very sceptical because they thought, well, surely if you blow cold air through hot metal, it's going to cool it down and it will just solidify in the furnace and wreck the furnace. And so lots of people were sceptical about about his suggested process, but they found that it actually worked. And you got this rapid oxidation of the rapid reduction of the carbon to carbon dioxide in the furnace, and you get this big flash of light appearing at the top of it. And then it was sort of refined by French engineer Pierre Martin later in the 19th century. And then they eventually were able to reliably produce carbon steel, what we call mild steel, in quantities that made it usable. And obviously the beauty of that was that whereas raw time was a very labour-intensive process, the manufacture of steel turned out to be much less labour-intensive, so of course a lot cheaper. So steel has a sort of between about 0.2 and 2% carbon content, and then there are often other alloying elements added to change its properties depending on what you want to use it for. And obviously the most obvious one we know about is stainless steel, where you're looking for something that's resistant to corrosion, where they add things like chromium and manganese to it. The thing that we noticed was that as soon as they were able to reliably produce quantities of steel, because of it as much less labour-intensive process, the use of raw time went into rapid decline. So within the period of about 30 years, raw time use basically collapsed as steel took over. And a couple of examples I always give is of that crossover point. One of the last big structures to be built with raw time was the Eiffel Tower in the late 19th century. And then one of the first big steel structures to be built was the Forth Rail Bridge about the same time, in the sort of 1880s to 1890, just at the point where these two materials are changing over. And we do find in conservation sometimes if we're working on structures from that period, often you'll find there's a mixture of wrought iron and steel in it, where they're using up odd bits of metal that they've got and mixing the two together. So from a material point of view, the things to look out for to help you with your identification of it, things like shape and design. Obviously cast iron things tend to be slightly bigger and more chunky, and obviously recognisable, repeatable shapes. And the thing with cast iron to remember is if you're looking at a building, is it's very good in compression, but it's no good in tension because it's very brittle. It would just snap in half. Conversely, raw iron is very good in tension, not so good in compression. So often what you notice is structures are built with a combination of the two materials as the Victorians realised the benefits of the properties of each material. So you would have things with cast iron columns supporting riveted wrought iron beams. Obviously, if you're looking at something iron and it's riveted, then the chances are it's going to be made out of wrought iron or possibly steel, and it won't be cast iron. And if it's sort of generally fine and delicate and decorative in shape, particularly if you're looking at gates and railings, the chances are that'll be wrought iron because it's been hammered and fire welded together. The other thing to look out for on cast iron is you often get porosity, particularly with old castings. If you can imagine when they first were casting the metal in the mould, as the metal goes in, the level rises, and then you get bits of rubbish and other things trapped at the top of the casting that don't come out through the vent holes, and that can lead to holes and porosity occurring in the metal itself. And often, because the Victorians and others were aware of this as being an issue, they were careful in how they placed their pattern into the mould so that that particular floor was in a particular place. The other thing is worth mentioning with cast iron is that if you're dealing with something that's big but fairly thin, it's much harder to produce a good casting, because as you imagine, as soon as you take that metal out of the furnace and start using it, it's cooling down. So if you've got a big thing that you're trying to cast, what you don't want is for the metal not to flow all the way through the pattern, all the way through the mould to give you your shape. So often what you find with big castings is they might have 3 or 4 or 6 pouring points with everybody pouring the metal in at the same time. So it all merges together in the middle to give you a nice quality casting. And one of the things I always cite is one of the hardest things to cast are gutters, because they're sort of quite thin and long. And it's very difficult to get the metal to keep its temperature high enough as it flows down towards the centre. So often if you buy cast iron gutters from a shop or a hardware store, they're always supplied painted. And the reason for that is because if you scrape the paint away, you'll find that there's filler in it where there's been imperfections in the casting and they've filled it and painted it. And often when, if you're working on a heritage project, the client will specify a paint system that you have to use, and they'll say, well, we want you to buy your gutters from this particular supplier. So you say, well, that's fine, okay. But then the supplier doesn't want you to take the paint off for their gutter because you'll see that the quality isn't really up to scratch. So sometimes it's an interesting conundrum that we have to deal with. So moving on, say a little bit about corrosion. Obviously that helps to our understanding of what we're trying to do to stabilise this material. And as I said at the start, because iron's an unstable material, it will readily oxidise in the air and in the presence of water to sort of almost take it back to its mineral state where it is a lot more stable. And that obviously that process we know as rusting, and it gives us that sort of red-brown colour. And there you can see, just for those of you that like a bit of chemistry, just the basics of what actually happens when the iron corrodes. And you end up with this iron oxide or ferric oxide. And obviously it's very dependent on the availability of oxygen and then moisture, which in the presence of electrons in the system gives you that electrolyte which causes that process to occur. And there is one particular scenario which causes iron to corrode much more significantly, and that's when you get salt present. So anything that's near a coast or it tends to be buried in the ground, you get penetration of salt, and particularly chloride ions, into the surface of the metal, and that is it significantly increases the process of corrosion, because if you can imagine, salt's hygroscopic, so it will draw moisture out of the air, and then the chloride ions go right down to the surface of the metal and are very difficult to remove. For those that like little chemical drawings, there we go. This is a diagrammatic version of what goes on. And then the other thing to be aware of is when you're dealing with metals is there's a sort of hierarchy of corrosion or deterioration that occurs, and those what are called electropotentials can be put into a table, and then you can see from that table that there are some metals that are much more noble and less likely to corrode than others. And you can see there that iron sits close, down closer to the bottom. So if you've got two different metals together, one of them will always corrode in preference to the other. And generally speaking, iron tends to be the victim of that because it's often connected to copper or lead or nickel and things like that. But you will also see that sitting below it is zinc and aluminium. And that's the reason why today a lot of iron and steel is galvanised. They put this zinc coating on it because we know that in that situation, the zinc will corrode in preference to the iron or the steel and give it much longer period of protection. The other problem with iron is that with a lot of metals, when they oxidise, the oxide film occupies the same volume as the metal that's corroding. So you get a nice film over the surface, which provides a protection for the surface against these corrosive elements, namely water and oxygen. But unfortunately, iron isn't in the same category in that the corrosion that's produced occupies 9 times the volume of the iron that's corroded. So if you see a piece of iron corroding, you end up with a huge amount of voluminous corrosion on the surface, which obviously doesn't provide a protective surface to stop this process from carrying on. And as I say, then in the presence of chloride ions, we get this ongoing corrosion where you get moisture forming hydrochloric acid and so on and so forth. It's very complicated and I won't bore you to death with it all. But there we go. The net result is that iron is very susceptible to corrosion. So as conservators, what we need to do is, in order to prevent that from going on, is to, where we can, is to exclude oxygen and exclude water. And then we know pretty much that corrosion won't occur. This is just an example of a vintage car, which I used to work for the Science Museum many years ago in their store, and we had a lot of vehicles in the collection that looked a little bit sad, where obviously the exposed ironwork was slowly corroding over time. So just to think a little bit about conservation and what it is, it's a sort of catch-all term that we use today, which describes all the measures and actions that we would need to take to safeguard any cultural heritage, not just metal, be it stone, wood, plastic, paper, and the idea is to prevent further change and damage over time, and it includes things like, loss and neglect as well. But within that broad categorisation, we tend to have 3 sort of aspects that we think about. We think about preventive conservation, which are things that we might do around an object to stop its deterioration. There might be a need for some remedial conservation where we're intervening in some way to stop a process of deterioration from carrying on. And then at the other end of the spectrum, we've got restoration, where you're restoring or reinstating something back to an earlier condition that it had, but perhaps it's lost it over time. And generally speaking, as part of the process of conservation, what we need first do is have a bit more of an understanding of the object we're dealing with, to help us decide what is the best approach to its preservation. And that normally involves a bit of research and obviously a bit more of a detailed examination of what it is, what it's made of, and what process of deterioration are going on. So to think briefly about preventive conservation, when we use that term, what we're talking about is the things that we can do to the environment that the object is living in, whether it be a piece of iron, a piece of paper, a photograph, that will change that environment to reduce or stop those deterioration processes from going on. And it can include things like, if you've got a piece of silver, for instance, don't handle it with your bare hands, because the acids and moisture in your skin will cause corrosion to occur to that silver, and you'll end up with permanent marks on it. We might be thinking about, watercolours or photographs which are very sensitive to light. The light has got, obviously, is made up of energetic particles, and those, when they hit the surface of something, some of the energy they contain gets transferred into that surface and is enough to cause deterioration processes to go on. And a lot of these things are irreversible. And then for things like metals and organic materials, we think about the amount of moisture in the air that they're exposed to. We know that if the moisture levels are high, metals are not very happy and they will corrode more readily. And by the same token, if we're talking about organic materials like wood and paper, they're more susceptible to mold growth and rot and things like that. By the same token, if the temperature is humidity is very low, things like metals are much happier. They won't corrode. But conversely, if you've got an object which has got organic materials on, they start to have problems because they're too dry. So it's about balancing those things to try and improve the preservation of the object without actually intervening physically into it. Example there is a Daimler belonging to the owner of Sunnycroft, which is just outside Telford, a guy who ran a Victorian tile factory, and that was his everyday runabout car. And they haven't really done any sort of intervention. It just is looked after by means of, preventive conservation techniques to try and stop it from deteriorating. Then we move on to remedial conservation, which is a bit more relevant to what has been going on at the town hall. Well, what we're trying to do is intervene to stop the deterioration processes from carrying on. And it may be also that you do have to do a certain amount of minor repair or reinforcement work to stop something from, maybe it's a bit unstable or whatever, to stop it from being at risk of deteriorating further. And it might be as simple as cleaning something to remove dust and dirt from the surface. For metals, obviously trying to stop corrosion from occurring. You might have an issue with acid build-up in paper, which causes it to go brown. So you need to de-acidify that to stop that from carrying on. Or if it's a piece of decaying timber, it might need a little bit of consolidation. For iron, it's normally a question of we have to remove some of the corrosion layers to stabilise that corrosion and then put some kind of protective coating on the surface to protect it from further deterioration over time. To give you an example, this is a cast iron, what we would call like an overthrow over a gateway down in Plymouth on the coast. So it's been exposed to sea air, salt for a very long time. So you've got this rather voluminous corrosion that's occurred on it. So with that, it was simply cleaned to remove that corrosion before a protective paint system was applied. And you can see actually there was a lot of the original detail still there. And most of that disfigurement was, voluminous corrosion, which hadn't really significantly altered the underlying appearance of the shape of the piece. And then finally, just to think briefly about restoration, those are all the things that we might do to something. Principally these days, it's done to help with its interpretation or understanding by people. If you've got a machine and there's parts missing, you might seek to have some pieces made or do something to it so that it helps people to understand what it did in the past. At the other extreme of that, you might think about somebody who has a vintage or a classic car and they restore it back to running conditions so that they can use it. That's a more extreme form of restoration. And today, certainly, we probably end up restoring cars to a better state when they left the factory, in the 1930s or 40s or 50s. For things like ceramics, it might be you've got a broken pot that needs to be repaired so people can understand what its shape and form was. You might have a glass vessel that needs some filling doing to it to help support it and help you understand its shape better. But the thing to remember is with conservation, it's normally a combination of all these three things. It's never normally just the one. So there might be a certain amount of restoration. There'll certainly be some remedial conservation, but then we would do something to recommend that this object goes back into this kind of environment so that the treatment that you've applied to it is longer lasting than it would be in the past, or at least that's what we hope. To give you an example, this is a cast iron plaque with a little bronze plaque underneath, which was looking a little bit sorry for itself, commemorating the bridge over the River Towie in Swansea. It was carefully removed from its surround, taken and cleaned and repainted. Not a huge amount of work really involved, but obviously it's brought back all the detail and people can now read what it says, and it's been stabilised. And as long as it's maintained in the medium term, it shouldn't deteriorate significantly. And then the one other thing to think about is what we call conservation ethics. Obviously, a conservator is a sort of professional and who's trained, and their knowledge, skills and experience and understanding help them to act to do the best for the cultural heritage that's in their charge. And these skills and that are underpinned by what we call ethics. So what we would try and do things which were acceptable and meet certain criteria. And so in order to be able to do that properly for any particular object, what we would do is look at it and consider various factors before we made a final decision about what we might do to it. And often with a lot of things, there's more than one solution to the problem. It's not a question of it's got this problem with it, this is what we do to it. Then there'll be a broad range of options, and the one that's chosen will be chosen for a particular reason. It might be, what are the effects that it's going to have on it when you treat it. Stakeholders are often very important. The owner of something, they might have a particular requirement for something which, if you put your pure conservation hat on, you might say, well, actually, that's probably not the best for it. But because this is what you want to do with it, then, we can approach it in this way instead and do the best that we can to meet the requirements that you want. But obviously you have the understanding that there are some limitations or restrictions that we need to think about. Also, if you're looking at something historic, at what point in its history do we want to preserve it? Are we looking at a particular time? Maybe there was a certain time when this thing had a particular significance, or are we trying to conserve it so that we're keeping elements of its history as well at the same time? Do you keep the original repairs that are done to it? Maybe something was conserved or restored 50 years ago. They used the best materials and techniques they had at the time, but obviously things have moved on in 50 years and we might think, well, now that's not such a good approach. Sometimes the materials that have been used are breaking down, or they might even be impacting on the object itself. So we would seek to take those away. But sometimes it may be that that's appropriate to be left as it's recording the history of what's been done to it in the past. One of the great things in conservation is always reversibility. In an ideal situation, you would want to intervene into something, treat it, and then 50 years in the future, somebody can come back and say, oh no, we don't like that. We'll undo that, return it to the state it was before you did it, and we'll do something else. Well, the reality is that's very, very difficult to achieve, particularly when we're thinking about ironwork, where obviously you're removing corrosion and applying protective coatings, let's say. In order to be able to do that, there's a certain amount of irreversible intervention that you have to do to be able to put that paint on successfully. There's also important to understand the skill of the person that's doing the work, and obviously ideally what you would want is the person doing the work would have all the necessary skills to do whatever's required, but that's not always the case. And then obviously any intervention into anything at all, there's always an element of risk involved in it. If you're repairing something or you're doing something to it, there is a risk that you could do some damage in the process. So that has to be factored in as well. And sometimes there might be a treatment that you can consider, but the level of risk to the object in terms of potential further damage is too high. So you may well then go for a lower kind of treatment option for that reason. And then the final thing to think about is what's going to happen to that object once you've finished it. Is it going to go outside to be displayed? Will there be any maintenance done in the future? Generally not. Will it be inside in a nice controlled environment, like a library or a museum? Will it go into an unheated store in a building? All these things will affect the decision you make about the treatment that you might apply to it. And then obviously it's always very important that whatever's done is always recorded and documented, so that in the future, when inevitably somebody will look at it again, maybe in 30 or 50 years' time, they will know what's been done to it, hopefully, and it will help them when they're coming to maybe to undo what you've done or to apply a new treatment to something. So generally when we're thinking about ironwork, we've got two options really. One of them is we know that if you can reduce the level of relative humidity or the amount of moisture in the air down below 30%, then that process of corrosion pretty much comes to a standstill. And the good example of that is the SS Great Britain down in Bristol. When they examined the hull of the ship, the piece that was below the waterline was really quite badly corroded. And if they'd gone to the extent of cleaning off all the corrosion and everything else, it would have been like a lace curtain. So the decision was that the better option would be to control the deterioration of that portion of the ship by reducing the relative humidity down to about 30%. So what they did was they put a glass plate around the line of the ship, between the ship and the dock, and they've got dehumidification equipment in there which constantly dries it all the time, and it basically blows dry air across the surface of the hull all the time. And it's been doing that for 20 years now. Obviously, it's quite expensive, as you can imagine, because bear in mind, there's also the dock walls, which are porous, so moisture's constantly coming in there as well. So as well as trying to keep the ship dry, it's also sucking moisture out of the surrounding river and riverbed. And the other big thing to bear in mind with that is the cost of that, running that equipment down at 30% relative humidity. So one of the things that periodically gets looked at is, well, if we increase that level slightly, let's take it up to 35 or 40%, we know we're going to get a certain amount of corrosion. Is that acceptable? What's that going to do to the lifespan of the ship's hull? Because obviously at some point in the future, it's going to be in a position where it's in a more perilous state. So these are all things that have to be thought about. Then the other option that we have is to put a protective barrier on the surface of the iron to basically prevent moisture and oxygen getting through to the iron, so in theory it won't corrode. And generally speaking, that's the solution that's done today, particularly for stuff that's outside industrial pieces and machinery and things like that, where you can't bring them into a building because they're far too big. So what we rely on is modern paint systems and coatings to give us a really good barrier to the surface. So that leads me on nicely to the town hall objects. Heritage Project contracts originally were contracted to do the rainwater pipes on the building. There are 106 runs of rainwater pipe, typically made up of about 16 sections of cast iron pipe or lead pipe or a mixture of the two. And each of those sections is about 6 foot long. So it's quite a lot of pipe work. They all had to be labelled and recorded and then carefully taken off the building and taken away to be treated off-site. There were two main types. The one thing you may have noticed on the film if you were beady-eyed was they had a date on some of those pipes, and a lot of them are dated to 1988. So they're quite recent from the previous phase of restoration of the town hall. And we know that at some point in the past there was more cast iron on the town hall, and then at some point a lot of that was taken off and was replaced with lead. Now, if you think about cast iron as a material and its function as a rainwater pipe, if it's not kept clear of debris and dirt, it blocks up. And then when it fills up with water in the winter time when it's cold and it doesn't drain, we get a cold spell and it freezes. What happens to ice when it freezes? It expands. So the cast iron cracks and breaks, and you end up with lots of flaws and damage in it. So maybe one of the reasons they moved away from cast iron a bit was because of that issue and the issue of maintenance. If you can imagine trying to rod a piece of pipe that's made up of 16 lengths of 6 foot, it's going to be quite a challenge. So anyway, as part of the works that back in 88, they obviously changed some of it to cast again. But there is still some lead. So there's a mixture now of lead and cast. And so Heritage Project contracts, we were working on both the cast iron elements and the lead elements as well, some of which were original lead. And there were 1 or 2 pieces of original cast iron as well. So these went back to the workshop. They were cleaned to move all the old paint and corrosion from the surface. And then they were acid dipped to put a passivating coat on them. And then they were painted with a high quality paint system, the sort of thing that's developed for modern industrial applications, because the town council were wanting a coating system that would last at least 30 years. Because as you can imagine, once the scaffolding comes down, it's going to be quite difficult to maintain some of those pipes. So they wanted something that's going to be really long lasting. So that was what's done for those. Now, also because there was issues to do with, access and maintenance in the future, where there were pipes that had areas of damage, generally speaking, they weren't repaired, they were replaced. So new patterns were made and replica pipes to the same detail were cast by a foundry, Hargreaves Foundry, based in Halifax. Yeah. So new castings were made to replace broken ones. At the moment, I believe you're about, is it halfway through putting them back? So about halfway through re-putting the pipe back on. As the scaffolding comes away and we've got access to the elevations of the building, the pipe runs are going back in again. What I should say is that the process of painting is quite rigorous, because we want to be sure that we've got the manufacturer's guarantee on the paint system. So the thicknesses all have to be to a certain minimum amount, and they all have to be checked and recorded. So every piece has been painted very carefully by hand, by brush and roller. And at each stage, the coating thickness was checked to make sure it was to the standard required. And if it was a bit thin, it obviously had additional paint applied to make sure that it met the standard. So the second bit of work that we've been involved in is the roof crestings on the town hall. They're a combination of cast iron and wrought iron. So generally you've got cast iron sections running across the ridges, and then the decorative elements on the top are made out of wrought iron, forged wrought iron, and then some of the finials are cast as well. But the roofing contractors were responsible for taking them, labelling them, taking them off. We refurbished and repaired them. We made some changes to some elements to improve the longevity of them and the way that they were fixed to the roof. They were all repainted in the same way as the rainwater pipes, and then they've been going back in batches and being refitted. So you can see there sort of batches of components. Generally, they were broken down into their component parts, and so that every face and edge and surface was painted properly and then put back together again. And then they were went back and put back on the roof. And you can see there some of the finished ridge crestings there, and another view inside the scaffolding. I think that was taken a couple of weeks ago, was it, Will? Yeah, of where we are with them now. I think quite a high percentage of those are now back on the roof again. And then one of the other big pieces of work which has come to us more recently is portcullis gates to the four entrances of the building. These are all late 19th century forged ironwork, and they all sit down below ground level. And originally they were wound up and down by hand, but then more recently they were motorised, so that at the press of a button they come up out of the ground and close the entrances to the building. They've been painted many times over their life, so there's probably 20-25 layers of paint on them. I think they were quite a challenge to get out, weren't they, as well, off-site, various lifting frames and things had to be made, and then obviously carefully moved out of the building. One of the things we did was we used a 3D laser scanning technique to record them in detail in the building, because one of the things that we had to do was upgrade the lifting mechanisms for each of them for when they go back in later. But you can see the decorative detail there under the paintwork's really quite nice. And generally they were in a very good condition. So they were cleaned by hand. Basically we used paint stripping materials to take the paint layers off carefully back to the ironwork. Then the iron was all finished by hand to a high level of cleaning before being carefully repainted again by hand using the same paint systems that were used for the other bits of ironwork. There were a small number of decorative elements that were missing. These were remade by a conservation blacksmith. We gave him examples of pieces that needed to be replaced, and he re-replicated them in his forge, and they were refitted. These gates are all held together by pins and dowels and screws and nuts and bolts, so they all sort of bolt together. And we're at a point now where they've all been finished painted, and they're all in their special frames for moving and transport, awaiting the return to the town hall in the not too distant future. And that, as we say, is all I've got to say. So thank you for listening.